Artificial intelligence, or AI, refers to computer systems that can perform tasks we associate with human intelligence. This video defines AI clearly and calmly. The goal is not hype, but understanding. What AI does, how it works at a high level, and what its limits are. AI is now part of modern infrastructure. It influences decisions and services in ways that are sometimes obvious and sometimes invisible. Understanding AI is useful because it affects information, work, and daily choices, even when no one labels it as AI. You will find AI across technology, business, science, and public policy. It helps automate routine judgments, detect patterns in data, and support decision-making. The same core methods can be applied in many domains, which is why AI spreads so widely. AI feels everywhere because it is mostly software. It can be embedded into apps, websites, devices, and business systems. Unlike a physical machine, software can scale quickly. Once deployed, it can influence millions of interactions with little visibility. AI feels everywhere because it is mostly software. It can be embedded into apps, websites, devices, and business systems. Unlike a physical machine, software can scale quickly. Once deployed, it can influence millions of interactions with little visibility. AI is misunderstood partly because discussion is polarized. Some people treat it as magic. Others treat it as a threat. Both views distort reality. The practical truth is that AI is powerful in specific contexts and limited outside those contexts. Fiction often depicts AI as human-like, conscious, emotional, and independent. Real AI is not like that. Real systems do not have inner experience. They do not want anything. They compute outputs based on training and design choices made by people. Confusion creates two kinds of mistakes: overtrust and underuse. Overtrust happens when people treat AI outputs as fact. Underuse happens when people ignore useful tools due to fear or misunderstanding. A clear definition helps avoid both errors. Definitions matter because they set boundaries. If you think AI is human-like, you will ask the wrong questions. If you treat it as a tool with capabilities and limits, you can evaluate it realistically, especially in high-stakes settings. A practical definition: AI is a machine capability for performing intelligent tasks, tasks that involve learning from data, recognizing patterns, making predictions, or supporting decisions. Notice this definition is about performance and function, not consciousness or personality. Here, intelligent means the system can do a task that usually requires human cognition. It does not mean the system understands meaning. It does not mean it reasons like a human. It simply means it can produce useful outputs, classifications, predictions, or actions. AI is not conscious and not emotional. It does not have beliefs or desires. When an AI system seems friendly, confident, or persuasive, that is a style of output, not an inner state. Confusing style with understanding is a common error. AI has no inner experience. It doesn't feel pain, curiosity, or pride. It also doesn't know things the way humans do. It processes inputs and produces outputs. That distinction protects you from overtrust and helps you design safer systems. Common AI tasks include recognizing patterns and making predictions. For example, detecting spam, identifying objects in images, or predicting the likelihood of a transaction being fraudulent. These tasks rely on patterns learned from historical data, not on human-like reasoning. AI also supports language processing and decision support. It can summarize text, classify documents, or help prioritize cases. It can also optimize decisions, like choosing a route or allocating resources, when objectives and constraints are defined clearly. Human and machine intelligence are different kinds of intelligence. Humans use common sense, lived experience, and flexible reasoning. Machines rely on computation and statistical learning. Machines can be fast and consistent, but they can also be brittle and context blind. AI is a field, Like medicine or physics, not a single tool. It includes research, theory, and engineering practice. Different methods solve different problems. Thinking of AI as a field helps you avoid the mistake of treating AI as one uniform capability. There is no single AI system. There are many systems built for different tasks, trained on different data, and deployed under different constraints. Two products, both called AI, may behave very differently. Always ask, which model, trained on what, used where? Some subfields focus on vision, such as recognizing objects or detecting anomalies in images. Others focus on language, such as understanding text, generating responses, or translating between languages. Each subfield has its own methods and limitations. Other subfields focus on learning, optimization, and control. Learning is about improving from data. Optimization is about choosing the best option under constraints. Control is about selecting actions over time, often in changing environments. These are distinct problem families. Traditional software is rule-based. Programmers write explicit instructions. If this condition is true, do that action. This approach is clear and predictable when the problem is simple and the world is stable. Many systems still work best this way. Rule-based systems are strong when you can list the rules reliably. They are transparent and easy to audit. If something goes wrong, you can often trace it to a specific rule. That kind of clarity is valuable in safety-critical and regulated settings. Rules become fragile when complexity grows. Real-world environments contain exceptions and edge cases. As rules multiply, interactions between rules become hard to predict. Maintenance becomes expensive, and the system can fail in surprising ways when conditions shift. This is the rule explosion problem. In messy environments, you cannot anticipate every case. The number of possible situations becomes too large. At that point, learning from data becomes appealing, because it can capture patterns without manually writing thousands of rules. Learning became necessary to handle uncertainty and variation. Instead of coding every exception, we train models on many examples. This doesn't guarantee perfection, but it allows systems to generalize across similar cases and improve when more data becomes available. Learning from examples means we provide training data and let the model discover patterns. For example, show many labeled images of cats and dogs, and the model learns features that help distinguish them. It's not seeing like a human. It's detecting statistical structure. Training is the process of adjusting model parameters to reduce error. The system makes predictions, compares them to correct answers, and updates itself to improve. Over many iterations, performance increases. This is fundamentally an optimization process, not a process of understanding. Most AI outputs are probabilistic. The system estimates what is most likely given the input and what it learned from data. That means uncertainty is always present. Treat AI outputs as informed estimates, not guaranteed truths, especially when the situation differs from training data. Prediction is not certainty. A system can be accurate on average and still fail on specific cases. Confidence also matters. Sometimes the model knows it might be wrong, but users ignore uncertainty. Good systems communicate uncertainty and users respect it. Prediction is not certainty. A system can be accurate on average and still fail on specific cases. Confidence also matters. Sometimes the model knows it might be wrong, but users ignore uncertainty. Good systems communicate uncertainty and users respect it. Data shapes AI behavior. A model learns what it is shown. If important cases are missing, the model cannot learn them. If labels are inconsistent, the model may learn confusion. Data is not just fuel, it is the foundation that defines the system's competence. Data quality issues include bias, gaps, and noise. Bias can reflect historical inequality. Gaps can reflect underrepresented populations or rare events. Noise can reflect measurement errors and messy collection processes. These problems don't disappear. They become part of the model. Poor data leads to unreliable outputs. A model might work well for one group and fail for another. It might perform well in normal conditions and fail during unusual events. This is why evaluation must test diversity, edge cases, and real deployment conditions, not only averages. AI systems do not understand meaning. They do not know what words refer to or what objects are in the way humans do. They map inputs to outputs using learned patterns. This can look intelligent, but it is different from comprehension. Pattern matching is powerful but limited. Correlations can be useful, but they can also be misleading. A model may learn shortcuts that work in training data but fail in the real world. This is why we test robustness and watch for failure modes after deployment. Most AI today is narrow AI. Systems designed for a specific task within a specific domain. Narrow AI can be extremely effective, but it cannot generalize across unrelated tasks. It does not become smarter in a general sense. It becomes better at its narrow job. Examples of narrow AI include search ranking, translation, speech recognition, and recommendation systems. Each is engineered to optimize a particular objective. These systems can be impressive, but their intelligence is specialized, not universal. Narrow AI has limits. It may fail when context changes, when inputs look different, or when incentives shift. It cannot transfer knowledge across domains the way humans do. That's why strong boundaries, monitoring, and human oversight are so important. Everyday AI often runs quietly. People see outputs, rankings, suggestions, alerts, but not the mechanisms. This invisibility can cause both overtrust and underawareness. When AI is embedded in systems, it can shape outcomes without being obvious. AI is increasingly infrastructure. It filters information, prioritizes attention, and influences resource allocation. These effects can be subtle, but they matter. Understanding AI includes understanding where it sits in broader systems and how it changes decision-making environments. AI appears intelligent because it can produce fluent outputs at high speed and scale. Humans tend to associate fluency with understanding, but fluency can be generated through statistical methods. The appearance of intelligence is not the same as the presence of comprehension. Humans also anthropomorphize technology. We attribute intentions and personalities to systems that produce human-like behavior. This is a natural psychological tendency. A good AI literacy habit is to separate what the system outputs from what the system actually is. Common misconceptions include the idea that AI thinks like a person, has goals, or acts independently. In reality, AI behavior is shaped by training data, objective functions, and deployment context. People remain responsible for design and use. Limits matter for safety, trust, and accountability. If an AI system fails, the consequences can be small or serious depending on the context. Understanding limits helps you decide where AI should be used, where it should be constrained, and where it should not be used at all. Humans are responsible for AI outcomes. Responsibility includes selecting the task, choosing the data, setting the objectives, testing performance, and monitoring behavior in deployment. AI does not replace accountability. It changes the form of work, not the need for judgment. Using AI well starts with clear goals. What decision is being supported? What errors are acceptable? What harms must be prevented? When scope is vague, AI projects fail or cause unintended consequences. Clear scope is one of the strongest safety mechanisms. AI capability always comes with constraints. Systems depend on data quality assumptions and stable conditions. When conditions shift, performance can degrade. Good practice anticipates change, monitors drift, and builds procedures for updating or rolling back models when needed. The core insight is that AI is a tool, not a mind. It can extend human capability in pattern-heavy tasks, but it does not replace human meaning-making, responsibility, or ethical judgment. Keeping this distinction clear prevents both hype and fear. Understanding enables better decisions. It helps you evaluate claims about AI, choose appropriate use cases, and recognize risks. It also helps you communicate clearly with teams, stakeholders, and the public about what a system can realistically deliver. At this point, you have a working definition of AI, a sense of how it differs from traditional software, and an understanding of its major limits. These are the foundations for everything that follows in the masterclass. Next, we will focus on a key distinction: why AI is not human intelligence. That comparison clarifies what AI can do well, where it fails, and why responsible use requires human oversight. With that, we continue building a solid, realistic understanding of AI.